Oh. Oh, we can always talk.
So, a general request. I would like to find a picture for this title slide. If anyone knows of a picture of Link from the Zelda games dancing, then I could use it and duplicate it and put it all over the title slide. And it would be great if I did this talk all over again. The current audience will just have to imagine it. So. Oh, already found it. That's perfect.
Ask Quiet Fanatic.
Oh, you found one.
So let's begin. This be the heckler section. Not the only one. How many of you have seen this game before? Oh wow. How many of you have solved it once? I have a confession to make. I hate Sudoku. I've never solved a single puzzle, but as of a few weeks ago, I've written a solver.
You've solved all of them.
I've solved all of them, but there's quite a few of them, so it takes some time to do it. So Sudoku, of course, for those of you who are not aware of what it is, which is none of you, it's about filling in numbers here, such that on each line all the numbers are unique, on each column all the numbers are unique, and in each of these boxes of 3 times 3 here, all the numbers are unique, from 1 to 9. And it's really a matter of ones and zeros. You could represent the constraint of putting one number in one cell of the matrix, in one cell of the Sudoku grid, with a line of ones and zeros in the matrix. Never mind how for now. Just believe that you can. And then it reduces to a well-known problem in computer land called exact cover. So what we're trying to do is to find a set of rows here that exactly cover this matrix. That means from the rows that we pick, in each column there is exactly one digit 1. Can you find one of these just by looking? Feel free to shout out if you find it. So the answer is not immediate. This is a hard problem. Sorry? 0, 3, 4. Yes, that's correct. 0-based. So the first column, the fourth, and the fifth, or rows 0, 3, and 4. That's correct. So how would a computer find this out? Find this unique solution 1, 4, 5, or 0, 3, 4? Well, one obvious way to do this is to just pick a column somewhere. Now we've sort of decided to go with this column. We have to pick either of the 2 rows that contain a 1 in that column. You see there's a 1 there and a 1 there in the crossing. And let's go with this one just to make things easy. Now that we've decided to keep this row, we are no longer interested in these columns because this row already has 1s in these columns. So we can pick one column twice, right? So these are out. We pick a new column, choose between these 2 rows, let's make this one, and the same thing happens. Now a few columns are non-reachable, and we do the same thing all over again. This gives us 3 choices, and we pick one. And you say, oh, this happens to be the solution, but Mäsak, you cheated. You knew the solution beforehand, and you went straight for the correct answer. And yes, I did. Oh, now you see all the columns are taken, which means that we are done. So that's the solution. I did cheat, and the real problem actually involves quite a lot of backtracking because you make a lot of incorrect guesses in picking out which row you want. And you have to choose every row that you can. So you end up choosing a number of rows. The total number of possible solutions is 2 to the number of rows because each selection of a row, yes or no, is a binary choice. And you do one such choice for each of the rows. So this is actually an NP problem, which means that your computer fan will start whirring when you try to solve it.
That's the nicest definition of NP.
Yeah. Yeah. Really, yeah. Thank you. So now the question comes, we have the algorithm, but how do we represent this so that it will be awesome and fast? So we take all the ones, you see how sort of made boxes around all the ones, and we keep those. We throw away everything else. You agree, of course, that this is still a complete representation of the matrix if we keep around the information about the location of these somehow. And we do this by tying them together. Here I've introduced a couple of column objects at the top, and the one over there is just the root. And then we tie everything together with linked lists. First horizontal linked list, tying all the rows together, including the column objects and the root. And then we tie them together vertically. So now everything is just a big mesh of linked circular lists going here and there. And this completely describes the 0-1 matrix. And it does it with basically empty objects just linking to each other. So why is this good? You will see that we require no memory allocations. We do the search entirely on this grid. So we allocate these few, a couple of dozen node objects, and then that's it. When I run this with the qualified moose, the algorithm stays put on 25 megabytes, which is basically nothing. It doesn't run away and scrap up a lot of memory. The project that I've been working on is try to solve Sudoku, but hide away all the nasty things about the 0-1 matrix that I just showed you. Because humans don't think in 0s and 1s, they think in nice graphical Sudoku grids. So we need a solver, yes. And the solver acts on the computer input, which is a 0-1 matrix, and it spits out a computer output, which is a set of solutions, each being a set of anonymous row numbers. That's totally uninteresting. What we need is something to wrap this. For example, a Sudoku reader accepting human Sudoku input, and a Sudoku writer translating the boring solution row numbers back into actual placement on the Sudoku board. And we can have several readers and several writers for various interesting problems which all map to the exact cover problem. The cake is a lie. I included this slide for Jonathan's sake. Well, it was. When I went through the slides very quickly doing rehearsal, Jonathan said, hey wait, did one of the slides say the cake is a lie? No, I said. Then I just had to include one to confuse Jonathan. So, during this project, in implementing this linked list representation, which can solve Sudoku and a number of other problems, I've been trying to find a common model for all those problems, how to think about them. And exact cover is like tiling your floor with parquet pieces, for example, or trying to tile a chessboard with pieces shaped in a certain way. Where the mapping becomes, in this 0-1 matrix, one column corresponds to a location, or let's call it a resource of some kind that you can occupy. And one row corresponds to a tile, sometimes a fairly strangely shaped tile. It's easy to see the tile relation with, for example, pentominoes, where you have 12 pieces of 5 blocks and you just try to fit them on the chessboard in various ways. Then they are actual contiguous tiles. But if you think of it in terms of Sudoku, for example, the tile actually doesn't hang together. You have the row and the column, yes, but then you also have a block, which is sort of a separate part of the tile. So when you place a Sudoku number, you grab 4 resources. You grab that number, you grab the row, you grab the column, and you grab the block.
So it's 3-dimensional.
Yeah, at
Otherwise,
least.
schematic.
Yeah. This linked matrix is always two-dimensional, but the mapping of the problem can be any number of dimensions that the problem permits. So pentominoes, apart from solving Sudokus, it also solves pentominoes. And the thing is that if you have 12 pentomino pieces, that's 12 times 5, that's 60. You can't really fill a chessboard with 64 spaces. So you just pick out a square in the middle of 2 by 2, and then you have something which can be covered by pentominoes. And there are, I believe, 65 solutions there if you remove rotations and flips, reflections. Thank you. And if I have time, I'll do a live demo of pentominoes because it's also the difference between L5 implementation and C. 8 queens is an interesting one. Here you have, if you think of the tiles in 8 queens, it's also a queen occupies a row, yes, a column, they call ranks and files, and it also occupies a diagonal, or 2 diagonals, basically, on the chessboard. But there's a difference between the space that it actually occupies, which is really, really taken, and the spaces that it threatens. It only really sort of softly occupies the threatened ones. So it's perfectly okay for 2 queens to threaten the same space as long as they're not threatening each other. But that is perfectly solvable with just a single tweak to the dancing things algorithm. We can say that after this column number, you just ignore that we can cover several, the same column several times, and it will solve the 8 queens problem as well. So I made a C implementation of this, of the solver, and then I tried the pentominoes problem, which in L5 moves takes 90 minutes to spit out all the solutions, 210 if you don't remove rotations and reflections. And then I spent a number of days writing a C implementation, and I was thinking, okay, maybe I'll gain a factor of 3 or 5, sort of clocking in on a number of minutes. It takes 8 seconds to run the C solution. So Perl 5 is really slow, guys. You should work on optimization. It takes 5 seconds if I quit having the need for outputting the solutions as it goes and just output them at the end. Then it's faster. So there's probably some latency in the terminal. So I have some time, so I thought I would do this live demo with live implementations and the C implementation of pentominoes. Let's see, terminal. Can you all read that? Should I increase the font size? It's good. Let's see. DLX simple, 5. And here we have pentominoes. And let's just run that. Oops. 5, that's fine. So it's our 5 solving pentominoes. It just scurries away solving the problem right away. And this the Perl 5 implementation will print the answers as it finds them. So keep in mind, this is an NP-complete problem. It's perfectly alright to be a bit slow and not finding solutions immediately. It basically has to traverse this gigantic tree of choices of rows and spit out something. While it's processing, I'll open another tab and change the script a bit. Instead of solving the problem, let's remove these bits. We'll just have the reader spit out a matrix for C. I think that's what I called it. Let's try and run this. Oh, this problem. And I should probably print it, right? Yeah, I don't know. Let's try that. Here it goes. This is the format that my C implementation accepts. You'll notice that this is not a matrix of zeros and ones, because I just output the places where the ones are located. So zero-based columns indicating the ones. you'll notice that it actually evens out. Why is that? Well, we have one type of pentomino, and then we have 5 places that it occupies on the board. So it's 6 columns. And there's some meta information with the negative numbers. Right, so let's just go to the C implementation. Oh, by the way, yeah, it's starting, the Perl implementation is finding solution plan. And you can see the action of the writer here, that it actually translates back the solutions to actual boards. I should have an SVG version of this also. But for now, there's an ASCII version. These are the actual pentominoes lying on the actual board with a hole in it. Now, let's run the pentominoes program. It still works. Let's pipe it into the C program. Solve. I should time that, right? Time. I should shut this off because it's taking processing. Here you go. It doesn't have a writer, so it'll just write the solutions as row numbers. But it's quite a bit faster. The other one takes 90 minutes. So, thank you very much. And I'll be happy to take questions if there are any.
Carl, can you please show your folder?
I can definitely. The C code or the Perl code?
Especially for C.
Okay. I'd just like to show the thing that I'm proud of. Here's the paper where Knuth talks about dancing links. This algorithm here is sort of pseudocode for doing the dancing link steps and covering and uncovering columns. The Perl 5 code, solver dancing links. I'll just edit anyway. The Perl 5 code is here, and you'll notice the structure. I chose variable names so that they would be the same. The structure here is very, very mirroring the structure of this one, except this one uses a Pascal-like or Python-like indentation. All the for loops and all the steps is almost line by line with the Perl 5 program. And I'll try to see how as well officially. I'm not a native C programmer, so you're free to laugh. Here it is. I'll find the central algorithm as well. I find C contains lots of boilerplates, and I'll be happy to take reviews of this code. Interpretation, that one is the matrix. Here it is. Here's the same code in C. So it's not a lot of code. You see it's doing the same thing, cover up a number of rows and columns, and recursing, and then uncover the columns. The nice thing about this is that with linked list you can cover up a column, and as long as you uncover it in reverse, you don't need to copy any information or something. You just operate on this linked list. The only constraint is that you have to uncover things in exactly the reverse order as you cover them. So that's why this algorithm is called dancing links, because it does this backwards and forwards dance. More questions?
Also, there are Perl 6.
Sorry?
And the program it also says there's a Perl 6 implementation.
Right, it will be released later today. I've written, the tests are there to run. I can push them now if you're interested. I should also say a bit about the differences between Perl 5 and C and Perl 6. The Perl 5 to Perl 6 translation, which I'm doing, it's so straightforward. It's really nice. I mean, we keep saying that these are 2 different languages, but if you know them both and you know which transformations you want to do, they feel automatic, and it's mostly a matter of removing some characters in Perl 6, moving things around in forward sometimes, removing parentheses, removing castings from arrays to scalars and back and so on. So it's a really nice work just to implement by porting, and you should all try it. Porting from Perl 5 to C is nerve-wracking for me, but as I said, I don't code in C generally. I find it funny that it took 3 times as long time, it's 5 times as long, and it runs between 2 and 3 order of magnitudes as fast. That's the equation you have when choosing between Perl 5 and C.
Well,
Yes?
I think one thing worth noting, I've frequently done this sort of thing with mathematical investigations of trying to optimize by rewriting a low-level language. I've often found that if I take my Perl code, say, do the C version, depending on the problem, it can be between 10 and 1,000 times faster.
Right.
However, at the point I then want to start doing some maths and come up with a clever algorithm and completely change the way the program works, I'm far better off doing that at the Perl level first,
Yes.
and then doing the calculation to see, rather than trying to do that directly.
I agree completely. So on the C level, the program moves fast, and on the Perl level, the programmer moves fast. That's the real lesson.
One thing I did once with a minesweeper solver, which was actually back before my Perl days when I originally wrote it in C. I rewrote it in assembler to get 2 times speed up. Then went back to the C code and by various algorithmic improvements over the course of a year or so, got a speed up of about 10 to the 8.
That's awesome.
And at each stage I was saying, oh, one more speed, let's rewrite it in assembler. And each time it was giving me times 2 when I rewrote it in assembler. And eventually I just gave up. It's hopeless doing it in assembler. I'm far better off putting my effort into improving the algorithm in the C code.
Oh, it's definitely a sort of a trade-off, and you have to know when to implement it in what language. Yes.
well,
Question at the back.
yeah, thank you. Will the Perl 5 version be released too?
It's already released. It's on GitHub. The Perl 5 version and the C version are on GitHub. The Perl 6 version you will see later today.
Just search after your name and I'll find it.
Yeah, GitHub masak dlx-sim.
Thank you.
Thank you very much.